All right, let's do it. So, first thing that we're going to talk about here is what's called the common ion effect. All right, so first of all, let's rewind in our brain what we discussed last time. We learned about how to use this new addition to our constants page, this KSP chart. And what this tells us is the equilibrium constant for taking something like, for example, cadmium carbonate. If we take this compound and put it into water, it will dissociate, but in a very, very limited way, right? This was a compound that we would have classified as quote-unquote insoluble. But what we learned about was all these insoluble compounds still to some extent will dissociate at least a little bit, right? In order to figure out how much that is, we would use this KSP value. All right, so for cadmium carbonate, we take this and put it into solution. It dissociates into cadmium ions and carbonate ions. The KSP for this reaction is just the equilibrium constant, products over reactants. But since my reactant in these reactions is always going to be this solid compound, what I have in my KSP expression is just the concentration of those two aqueous products. And that does equal this very tiny number, 1 times 10 to the negative 12. Okay, but that's not 0. Right? So to some extent, this compound will still dissociate, just a really teeny, tiny amount. All right, so the common ion effect is now if instead of placing this cadmium carbonate into a solution of pure water, what if I placed it into a solution that had one of these, let's say, carbonate ions in there? So now let's say if my cadmium carbonate was added to a solution of sodium carbonate, which is considered a soluble compound. Can't spell today. Soluble. Would we expect more or less cadmium carbonate to dissociate? All right, so if I increase the concentration of my product, the carbonate ion, according to Le Chatelier's principle, what is that going to do to my equilibrium? Is it going to shift it in favor of the products or in favor of the reactants? So if I increase my product, it's going to shift it the other direction. Right? I'm going to get more solid cadmium carbonate. So I would expect that my cadmium carbonate would dissociate even less in a solution of carbonate, of a solution of sodium carbonate, than it would in pure water. All right, that is the common ion effect. These insoluble compounds are even less soluble in a solution containing common ions. And what do I mean by common ions? All right, the ions in that insoluble compound. All right, cadmium carbonate has a common ion with sodium carbonate. Both carbonates. All right? So they share that common ion, which is why my cadmium carbonate is even less soluble in this solution here, right? Because they share that common ion. Okay? So we can kind of prove this to ourselves quantitatively. We can do another problem where we calculate concentrations and see that indeed we get a much tinier concentration in this common ion solution. So for the sake of practice, let's use this same reaction. We got our KSP of cadmium carbonate. Let me make sure that I actually grab the right value. Okay, cool. 1.0. All right, so what we learned how to do last class was let's figure out what is the molar solubility of cadmium carbonate. All right, we got to figure out what, let's say, when added to pure water, right? All right, so remember, we're going to create a nice table. We have our solid cadmium carbonate, as well as our concentrations of cadmium and carbonate. And remember, one of the tricks to this problem was I didn't in the problem tell you that you had some initial amount of cadmium carbonate, because it doesn't matter. Doesn't matter whether you start out with 1 gram or 100 grams, you're going to get the same molar solubility. Let me actually bring over my chemical equation as well. All right, my solid cadmium carbonate is a reactant. Should it be going up or down in this reaction? Down. So I'm going to consume my cadmium carbonate. My products, the cadmium ion and the carbonate ion, are they going to go up or down? Up. And I have to account for that stoichiometric coefficient, although in this case, they're both 1, right? So this would just be plus x and plus x. Okay, so then over here, I get doesn't matter minus x. Again, it doesn't really matter because this doesn't appear in my KSP expression at all. What does appear is these two concentrations. So then I need to plug in my concentration of cadmium into my KSP expression up here, and my concentration of carbonate into my KSP expression up here. So what I get is that x squared equals my KSP value of 1 times 10 to the negative 12, which means that x, my molar solubility, is what? 1 times 10 to the negative 6. All right, so now we're going to do the exact same problem, but instead of adding our cadmium carbonate to pure water, we're going to add it to a 0.1 molar solution of sodium carbonate, which again is a soluble compound. All right, so again, I'm going to build my ice table. The amount of cadmium carbonate I start with doesn't matter. What's going to be different about this problem is that while I still start with 0 concentration of cadmium ions, what's the concentration of carbonate ions that I'm starting with? That's 0.1. Right? So it's not going to be 0 in both boxes, because in this problem I'm telling you that we're going to dissolve this into a solution of 0.1 molar sodium carbonate. Our change is still the same. My reactant's going to decrease. My products are going to increase according to their stoichiometric ratios, which again in this particular problem is just 1 and 1. All right. But now I have X is my cadmium concentration, and 0.1 plus X is my carbonate concentration. I'm again going to take these equilibrium values, plug them back into my KSP expression. So I get X times 0.1 plus X equals that KSP value. And we could use the quadratic equation to solve this particular problem, but what do we know about the size of X? Is it going to be a big number or a little number? I mean, it was really, really tiny. We did it in the best case scenario. It was 10 to the negative 6, right? Or 1 times 10 to the negative 6. And this time it's going to be even smaller because I have this common ion solution. So X is a super itty-bitty number. So what we're going to be able to do, similar to what we saw in our weak acid, weak bases problems, so we're going to be able to say that this is about the same thing as X times just 0.1. All right, we can assume that this right here is going to be so small, it's going to change that number almost, very, very small amount, right? You can just convince yourself right now by punching into your calculator, 0.1 plus 1 times 10 to the negative 6. That's basically the same number as just 0.1, right, from a mathematical standpoint. So X is so tiny that we can just assume that this is going to, that 0.1 plus X is just the same thing as 0.1. And again, just an assumption that we're going to make because it makes our life easier from a math standpoint. Right? Now when I solve for my molar solubility, I solve for X. I'm doing now 1 times 10 to the negative 12 divided by 0.1. Whoops. And I get a molar solubility of 1 times 10 to the negative 11. All right? So when I had pure water, I was able to get 1 times 10 to the negative 6 moles of cadmium to dissolve in a liter, which is not a large amount, right? A very tiny amount. But when I have a solution with a common ion in there, that decreased by like 5 orders of magnitude, right? Went from 1 times 10 to the negative 6 to 1 times 10 to the negative 11, a super teeny tiny number, okay? So again, the whole point here is this common ion effect is that ionic compounds are even less soluble in solutions containing a common ion. right? And we were just able to establish that quantitatively in that particular problem, starting out with a solution that didn't just contain 0 moles of carbonate, but contained that 0.1 molar carbonate. All right, so let's just do another one. Let's take another one of our compounds here, and we're just going to practice this. Calcium hydroxide. Okay, so what is, now I'm not asking for the molar solubility, but the actual concentration of hydroxide ions. In when calcium hydroxide is placed in a solution of 1.5 molar calcium chloride is considered a soluble compound. All right, so again, we're going to do our balanced chemical equation. Calcium hydroxide dissociates into calcium ions and hydroxide ions. How am I going to have to balance this chemical equation? What's missing? I need a 2 out front of that hydroxide. You're going to build me the KSP expression, and then finally construct that ice table. Right. Importantly, now in my KSP expression, my hydroxide ion concentration is going to be squared because there's a 2 in my balanced chemical equation. When I start out my problem, I have 0 moles of hydroxide in solution, but I have 1.5 molar calcium because of that calcium chloride. Reactants go down. My product, calcium, goes up by X. But what's going to need to go here in my hydroxide ion box? 2X, because of that 2 in my balanced chemical equation. So I get 1.5 plus X times 2X, or rather, and 2X. Plug those back into my KSP expression. I get my KSP equals 1.5 plus X. And then this is the easiest part to mess it up. I need to plug in 2X for the concentration of hydroxide, which means that that whole 2X gets squared. Again, because X is going to be tiny, I get to assume that this here is negligible. So this is the same thing as 1.5 times 2X squared in parentheses. Okay, that equals my 4.68 times 10 to the negative 6, my KSP for this compound. Distributing that X squared, this would be 1.5 times 4 times X squared, or 6X squared equals 4.68 times 10 to the negative 6. Whoops. All right, rearrange that and solve for X. I get X is 0.000883. We'll leave it at that. All right, so am I done? No, why not? What I found was the molar solubility, right? X is the molar solubility. How many moles of this calcium hydroxide are going to dissolve per liter, right? That's what X tells us. But what did I ask for in the problem? Hydroxide concentration, which according to my ICE table is not X, but 2X, right? So in order to finish this off and actually solve for what's being asked for, I have to take X times 2. And so my concentration of hydroxide is 0.00177. All right, so again, when you're doing your ICE tables, it's really easy to get lost turning numbers into new numbers. You always want to take a step back and make sure that you sort of understand what you just solved for. Right? In this case, X is always going to be my molar solubility. But if I want the concentration of hydroxide, I have to use 2X. Because according to my ICE table, that's what hydroxide concentration is. All right. So our last type of problem for this section, for this chapter, for this whole unit actually, is what are called selective precipitation problems. All right, So let's say we have a solution of 0.100 molar calcium ions and 0.100 molar, what did I just find? Cobalt ions. All right, we have a solution that's a mixture of both of these cations. We titrate in some sodium hydroxide, which is, of course, a soluble hydroxide compound. And we want to know which metal ion precipitates first. All right, so we got this solution. It's a mixture of calcium ions and cobalt ions. We're going to start to add in some hydroxide, some sodium hydroxide. And we're going to ask which one of these two metal ions is going to precipitate first, the cobalt or the calcium. All right, so first of all, we need to go to our KSP table. If we do have cobalt or calcium precipitate, what is it going to be precipitating with? The sodium or the hydroxide? The anion, right? The hydroxide. So we're going to look up calcium hydroxide, which we actually just did. That was this one here. That 4.68 times 10 to the negative 6. And now we're going to look up cobalt hydroxide. That's this one here, 5.92 times 10 to the negative 15. So let's get these both over here. Don't freeze. Technical difficulties. Hold up. Oh. Sorry, Patricia. Not this class. All right, crap. So again, calcium hydroxide, grab this entry. Oh my God. Cadmium hydroxide, or no, cobalt hydroxide, grab the other entry. Cool. All right, so we want to ask ourselves again, which one is going to precipitate first, the calcium or the cobalt? So we got to look at these two values here. According to these KSP values, which of these two compounds is the least soluble? Which am I going to have the, exactly, right? The smaller that KSP value, the more insoluble that compound is. If you just look at that KSP expression, it's the product of those ions, of those, it's the product of those products, right, in that reaction. And so the lower the number, right, the smaller the KSP, the less soluble. All right, so which compound is going to precipitate first? Cobalt. will precipitate, PPT first? All right. I can also ask, at what concentration of hydroxide will cobalt precipitate? All right, what I want you to do is to build your KSP expression for cobalt hydroxide, cobalt 2 hydroxide. All right, here's my KSP expression for cobalt hydroxide. And let's just look at this formula here. What do we have from our constants page from this formula? We got our KSP value. And what else do we have in this problem? We know the cobalt concentration, right? That's the whole premise of the problem, is that we have a solution with cobalt ions in them. So what's the only variable missing from this equation now? The concentration of hydroxide ion. I don't even need to do an ice table, right? I only got one missing variable in this problem, which is that concentration of hydroxide. So I'm just going to plug everything in and solve for that hydroxide ion concentration. Again, my KSP is that 5.92 times 10 to the negative 15. My cobalt ion concentration was given in the problem as 0.100 molar. And then what I don't know, I can leave as my unknown X, is that hydroxide ion concentration. All right, so that means that X, my hydroxide ion concentration, holy crap, super tiny number. All right, so 0.000000243, or, more condensed, 2.43 times 10 to the negative 7. How did I get what? Because that was what was given in the problem. All right, so that is my concentration of hydroxide when cobalt precipitates. At what concentration of hydroxide will the calcium precipitate? All right, I want you guys to try to solve this one for me, given what we just did, but real quick. Should it be a bigger number or a littler number than what we got for cobalt? Bigger, right? It's got to participate later in this titration, so I'll have added more hydroxide. All right, so again, I got basically the same problem here where my calcium times my hydroxide squared is equal to 4.68 times 10 to the negative 6. In this problem, I know my calcium ion concentration. The only thing I'm missing is my hydroxide ion concentration. Okay, rearrange, and I find that X is equal to 0.00684, or 6.84 times 10 to the negative 3 molar. And we can see that that is indeed a larger concentration, a higher concentration than what we saw for cobalt, which again makes sense because we said that cobalt was going to precipitate first. All right, so then lastly, what I can ask you would be if calcium's precipitating, so the concentration of hydroxide is now that 6.8 times 10, 6.84 times 10 to the negative 3 molar, what must the concentration of cobalt ion be? All right, so first of all, do we think it's going to be bigger or smaller than the original value of 0.1 molar? Smaller, in fact, quite a bit smaller, right? I had to precipitate out a whole bunch of cobalt before that concentration of hydroxide was able to rise and precipitate out that calcium. So now I'm going to use this KSP expression for cobalt again. Times that hydroxide ion concentration squared. Again, I know the KSP of cobalt hydroxide. This time I know my hydroxide ion concentration because calcium's precipitating. So what I'm trying to find is that cobalt concentration. What was it, 15? And what we would find is that my cobalt ion concentration started at 0.1, but at that point that these calcium ions are starting to precipitate, now it's all the way down at 1.27 times 10 to the negative 10, right? I had to react a ton of that cobalt ion before my concentration of hydroxide could rise to the point where my calcium was actually able to precipitate out. Right? So now I have very, very little cobalt left over in this solution. All right? Right? So if we have a mixture of these two metal ions, the one that's going to precipitate out first is going to be the one that has the lower KSP with whichever anion that we're adding in there, right? Because that means that it's even less soluble. All right? And we can quantitatively determine at exactly what concentration it will start to precipitate out. All right, so congratulations, you have now made it, through the second unit of new material in this course. All right. I just want to kind of take a step back and talk a little bit more about titrations real quick because, again, they're just super important for this particular chapter. All right, so remember we have these 4 different regions in our titration curve. That initial point here, all right, where that's just, in this case, a solution of weak acid. All right, so this is all weak acid. We then get to the equivalence point of our titration, which is when all of that weak acid has reacted. So at my equivalence point, I'm left with a solution of just what? If I've driven this reaction now all the way over here, I'm left with just my products, which are water and a weak base. All right, so that's my approach to calculating pH in these 2 regions. First is just for a weak acid, and then for a weak base. And this middle region here is a mixture of weak acid and weak base, which we again called a buffer. All right, and that very much so dictates our approach for how we calculate pH in these different regions. Okay? All right, one other thing that I want to point out is this little curve here. This is the signature of a weak acid strong base titration. Okay, because remember, our buffer region is fairly narrow within plus or minus 1 pH unit. So at the very beginning here, there's actually kind of a large uptick in pH that then levels off and gets much more slow because I'm not quite in my buffer region yet, right? So within this part right here, I get a much steeper increase in pH, and then all of a sudden it starts to level off and go more slowly. And that's because right here I'm not yet into that buffer region. Remember, we said buffers have only a sort of limited range in which they're effective, and that range is plus or minus 1 pKa. So I'm not quite there yet here. Right? That's also why at the very end I see a very steep increase before I get to my equivalence point, because now I'm outside that buffer region. But then in the middle here, we're in that buffer region. It's much more gentle of a slope, much closer to horizontal. So that's my buffer region in the middle. Okay. If we were going to do a titration curve for a strong acid, strong base, what we see is a much more sort of sharp S-curve here, where they start at a very low pH, right? A 1 molar solution of hydrochloric acid has a pH of 0, right? Very, very low pH. And then it remains relatively flat before all of a sudden shooting up and then leveling off again. All right? And it levels off at, of course, a very high pH, because then we're left with just strong base. Right? So in this region here, our sort of strategy for calculating this is excess of strong acid. Our region at the end is then an excess of strong base. And the equivalence point of a strong acid, strong base titration, if I ask you for the pH at the equivalence point of a strong acid, strong base titration, that's about the easiest question I can ask you. No math involved, because the answer is always just 7, right? That will not be the case for a weak acid, weak base. Or for a weak acid, strong base, the pH will be a little bit higher because I have that weak base solution. But for a strong acid, strong base, always 7. Okay? Now, what if instead I started out with strong base and I titrated in a strong acid? How would we expect that curve to differ? It's going to be the opposite, right? It's going to start out at a really high pH and then come crashing down and then level off at a very low pH. Again, I'm going to start off at some high pH value, level off at some low pH. But again, since it's strong and strong, that equivalence point is still 7. All right, so again, these pH problems are great for practicing all the various pH skills that we need from this particular unit. I'm still working on the answer key for that worksheet. I will post it by the end of the day, all right? There is that video, though, that walks through yet another set of problems that are slightly different for the worksheet, so you can always study that in the meantime.